Hello everyone. In this video, we are going to talk about principal moments of inertia. So in my previous video, I told you everything you needed to know about calculation for moments of inertia, but there is one topic that I wanted to discuss separately, and that is principal moments of inertia. So if you remember the moments, the second moments like ixx, ixy, and the product, they depend on the location, right? So ixx was what? It was integral of over surface of y squared dA. So you pick some element dA and then you moved it all over the surface, you sweep the surface with it, and you measure the distance y, which is from the wherever that element is to the x-axis, this one, and you squared it, multiply by dA, and integrate it, correct? That would give you ixx. Now, if I rotate my coordinate frame, so if I go from frame xy to frame x prime, y prime, which is acquired by a rotation about z-axis by angle theta counterclockwise, then you clearly can see that the y that you have here for this surface is going to be different, right? Because in this case, it's going to be ix prime x prime. It's going to be integral of y prime squared dA. So now you need to square the y prime, and y prime, as you can see clearly, is this distance. So that is y prime, this is y, and clearly you see y prime in this case is smaller than y, and maybe in other areas is bigger. So when I change the coordinate frame, whether move it or rotate it or both, clearly my moments will change because they depend on these positions. So what we need to look at right now is what happens if you rotate the coordinate frames, right? If you translate it, clearly you know how to calculate it. Use the parallel axis theorem. But what we care about is rotation. And rotation about which point? About the centroid. So here we want to know that at which orientation, at which theta, these moments are going to be their maximum values. Now, of course, if you make one of them maximum, you expect the other one to be minimum. And you might say, why is that? Well, because some of them, remember, some of these ixx and iyy, if you remember, was that polar moment Jo, which was the integral of r squared dm, and r squared was the radial distance. And in both of these cases, whether it's rotated or not, the radial distance is the same because the origin has not moved. So I expect that ixx plus iyy stays the same as ixx prime plus iyy prime. And both of them should be equal to Jo, because Jo is not going to change. It's not a function of x and y, it's a function of r, and r is not changing. So if one of them, because of this rotation, one of them goes up, since the total sum is constant, the other one should go down. And what happens to the product term? Well, while here for the xy frame, ixy is equal to 0, why? Because the shape, this ellipse, is symmetric with respect to x and y. But if you look at the x prime, y prime, clearly you see that it's not 0. Because with respect to the x prime, y prime frame, the shape is not symmetric. You see that with respect to x prime, y prime, it has more things in the second and in the fourth quadrant rather than first one and the third one, right? So this is the first one, this is the third one, and clearly you can see that in this case it has to be negative. So all of these all of these second moments will change. Now the question is, how do they change? How do they depend on the original values and this angle theta? This is what we want to find. And then we want to find the theta, the angle theta for which these moments, one of them becomes max, one of them becomes min, and you'll see that this product term will become 0. So if product term is 0, that means already one of them is max, one of them is mean. So in this case, actually, in this example here, the x and y axes are already the principal ones. Why? Because with respect to the xy, the product term is already 0, and in this case, iyy is maximum and ixx is minimum. Okay? But if the shape is more complicated, it's not as simple that you can just visually see that. And we have to calculate that. We should have formulas for it. So in order to do that, first we need to know the relation between x prime, y prime, and x and y. How are they related? Well, from a simple geometry, you know that x prime and y prime are related to x and y by this rotation matrix. This is a rotation matrix about the z-axis, but transposed. And it takes your old frame to the new frame. So, and you can see that easily through geometry. So x prime is basically, if you expand that, your x prime is x times cosine theta plus y times sine theta, and y prime is negative x sine theta plus y times cosine theta. Okay, so this is the relation between them. Using that, now I can calculate my new moments, x prime, which you might just show it with a single x prime. What is this? Well, this is integral of y prime squared dA. For y prime, I replace this formula, square it, and then I expand this. This is a plus b squared. So you're going to get a squared and then plus 2ab plus b squared. And now these theta terms, they are constant because theta is a fixed angle. You can take them out of the integrals. They do not depend on x, y, or a, so you can bring them out. So you're going to get sine squared integral of x squared minus 2 sine cosine integral of xy plus cosine squared integral of y squared. And you know this guy is your iyy, this one is your ixx, and this guy is your ixy. So you're going to get this. And if you use half angle formulas, then 2 sine cosine is sine of 2 times angle, sine of 2 theta. So you get this. And then for sine squared and cosine squared, if you replace them from trigonometry, as you know, cosine squared of theta is 1 plus cosine of 2 theta over 2. And sine squared of theta is what? It is 1 minus 2 cosine of 2 theta over 2. So if you replace them here, then these xy terms will be written all in terms of cosine of 2 times angle, and you'll get this. There is a constant term, there is a term that depends on cosine 2 theta, and there is the product term that is multiplied by sine 2 theta. And this is the average of those two, which, by the way, you know is a constant because this is your JO, this is your polar moment. So that is half of JO, the constant term, and then the difference between them divided by 2 cosine theta minus ixy sine theta. This is what? This is ix prime x prime. Using some similar algebra, you can find y prime, which is x prime squared. And for x prime, again, we are going to use this formula. Again, expand it and do the sine squared cosine squared formula I showed you, and you get this one. So look, now you got formulas for x prime and y prime. You got both of these written in terms of the original values and, of course, the angle. And if you look at them, what's the difference between these two? The constant term is the same in both of them. These two signs and those two signs plus and minus are swapped. So if this is a plus, here becomes a minus. If this is a minus, this one becomes a plus. That's the only difference between them. Now, ix prime, y prime. For that, first we need to know what is x prime, y prime in this new frame. So I replace x prime and I replace y prime. So I have to multiply and I get this big of a thing, and I can factor out here the sine cosine term, which you see it here and here. You get that, and then these two terms, they both have xy in them. You factor out xy, you get this term. So now you plug that inside dA, and these are two separate terms, so we can separate the integrals. This is going to be your first integral for that. This is going to be your second integral for this. And again, remember sine cosine and cosine squared minus sine squared, they can be taken out of the integral. Now this is half of the sine 2 theta, this is cosine 2 theta. Okay, so if you write them, you are going to get this. That your product term is just that subtraction term, the difference divided by 2 sine 2 theta, plus the product term times cosine 2 theta. There we go. So now with these three formulas, I could find all of the 3 second moments in this rotated system. Now, what is the principle? Clearly, we can plot them as a function of theta, and we can see that based on theta, these values will change. Even if these initial ones are constant, they are both functions of theta. So when you change theta, you expect one of them to go up, you expect the other one to go down, and this product term also will cross some numbers, right? So actually, let me plot that for in MATLAB for you. Okay, so here is the small code that I just wrote for it, and I just picked some numbers for x, y, and xy. You can pick any other number, but it's not going to change the overall behavior. It will change their initial value, but the overall behavior is the same. So if you look, when I plotted these three values, you see that when x prime is at the bottom, y prime is at the top. Okay? Right? Because again, remember, sum of them is a constant number. So clearly, sum of them is going to be equal to 9. So if one goes up, the other one goes down. So if you expect when one of them becomes maximum, the other one becomes minimum. And the other thing is, you see that when one of these becomes max or min, what happens to the product one? If you look at their max or min, so if I pick this point where this corresponds to basically maximum, minimum of this, and if I pick another one, which is kind of maximum of this one, right? And then if I pick something like 1.269, look, here you go. You see that this one is almost at 0. So when those two become max and min, this one becomes 0, and you see there is a 90-degree phase difference, right? So, and you can see that why, because these two are cosine sine, this one is sine cosine. So this product moment is always 90 degrees ahead or behind those two, and since they are harmonics, when those become max and min, this one is at the root, it is 0. So this point is where we can define as the principal moment, where the product is 0 and one of those two second orders is max, the other one is the mean. This is what that is the definition of principal moment. There we go. So this is what we have, and you can clearly see the definition of the principal moment. I just added these constant numbers in the title, so you can see these are generated with what initial values. So to mathematically find at what angle you have the principal moments, as I said, you set the product term to 0. So ix prime, y prime, you set it to 0, and you solve for the angle. Clearly, you divide by cosine 2 theta, you get tangent of 2 theta, and theta p, the angle for the principal plane with respect to the x-axis, tangent of 2 times that angle is given by 2ixy divided by ix minus iy. That is the angle using which you can have what? Using which you can have the maximum, basically x for one and minimum for the other one. Now, if I go back and look at this code that I have, So if I want to calculate that angle, if I say theta underscore p equals what? Equals 1/2 of, or arctan d of, since these angles are written in radians, let's just use arctangent of and divided by 2. And the numerator, you see, is 2ixy divided by ix minus y, or it's basically, if you want to know, it's this term divided by this one. When you divide that, 2 comes to the numerator. Okay, so 2ixy divided by the difference, so 2 times ixy divided by the difference between ixx and iyy. This should be the angle. And if we calculate this angle, how much would that be? In this case, you see 29.4 radian. And if I convert it to degrees, then you see the answer is basically 16.84 degrees. So if there is a profile with this ix, iy, and ixy, you have to rotate it 16.8 degrees counterclockwise with respect to x-axis to get it to principal moments. And you can just plug in into this formula 16.8 degrees, or 0.294. If you plug in 0.294 into this product term, you should be able to get 0 for the product term. So this is doing it in 2D and finding the principals. Now, by the way, how much are these max and min? So at the principal, at the theta p, the product term is 0, okay? So your inertia tensor, if you look at your inertia tensor, it is going to be some I1 and I2, and your product terms are going to be 0, so your I is going to be diagonal. So another way to say it is to say your inertia tensor becomes diagonal at the principal values. Now, how much are these min and max? They can be acquired by replacing this theta p angle into the formulas for xx prime and yy prime, and these are those numbers. So if you look at them, they both have the average of the ix and iy plus and minus the square root of what? The magnitude of this vector, which is this term squared plus this term squared under square root. And of course, the one with, because this term is positive, the one with plus is going to be the biggest one. The one with minus is going to be the smaller one. Okay, so you get the diagonal inertia matrix. Now, there is another way to look at this problem, which is really useful, and you can do it nicely, is if you look at it in terms of what we call eigenvalues and eigenvectors. And this is one of the places that you can use eigenvalues and eigenvectors. So what you will do is you form the inertia matrix, which in general is ix, iy, negative ixy, and negative ixy. And here you have to use those negatives. And then find the eigenvalues and eigenvectors of this I matrix. So in order for that, you do I minus lambda times the what I. This is the I of identity, not the I of the inertia matrix. Determinant of that, set it equal to 0. So that is the identity matrix. This is this inertia matrix in general, which is like ix, iy, and negative ixy in general. And find the eigenvalues of that. Now in 2D, you're going to get two eigenvalues, lambda 1 and lambda 2. And if you look at lambda 1 and lambda 2, which are the roots to this quadratic equation, these are going to be lambda 1 and lambda 2, which is coming from solving this quadratic equation. And if you compare these two together, you see they are the exact same thing. Here, you just need a little bit manipulation, you exactly get that. So what does it mean? It means I1 and I2, the maximum and the minimum moments, are the eigenvalues of what? Of the inertia matrix. Okay, that's what I said. These are the maximum and the minimum. What about the angle? How about this angle? How do you find this angle? Which direction is corresponding to max and min? That comes from the eigenvectors. So if you have the eigenvectors, the direction corresponding to the eigenvectors, one of them is the direction for I1 or lambda 1. The other one is the direction for lambda 2 or I2. That's all it is. So we can find them by the eigenvalues and eigenvectors. And to demonstrate that for you, here I found this theta angle. Now I also would like to find I1 and I2 in MATLAB. Okay, see how much is I1, how much is I2, and then I'm gonna repeat these calculations using eigenvalues and eigenvectors so you see the difference. So I1 and I2, let me type the formulas. So these are those formulas. Let's run, see how much we get. So you see at max you can get to 6.3 and your min is about 2.69. So your maximum moment can surpass 6. And of course it is because here you are not at the principal. Here this guy is not 0. So you see I1 is this, I2 is that, and this is the angle, 16.8 degrees, correct? So we found them by what? By the formulas that we had from trigonometry. Now we are going to do a different thing. So here we form the I matrix. And we say I matrix is what? Is Ixx, negative Ixy, negative Ixy, and Iyy. Okay, you form this matrix, and then you use the command eig. You say V and D, or lambda if you want, call it. V and lambda equals eig of the I matrix. Okay, so let's see what we get if I run this. So look at the lambdas, 2.69, 6.3. Are they the same as these? Absolutely. So you see the eigenvalues of the matrix are the maximum and the minimum second moments. Now you might say, what about theta p? What about this angle? Can you get that? Well, yes. Here, one of these columns, the first column corresponds to this number, and the second column corresponds to this number. Okay, what angle are these? So if your vector is negative 0.289i, negative 0.957j, what's the angle for this vector? Can I find it? Well, let's find out. So here we say I min, let me just write that, I min is equal to the min of diag of lambda, because when you say diag of lambda, it only gives you these two numbers, and when you say min, it should give you the minimum of the two. So let's see, you see here, that is your I min, and then I can do I max, which is the maximum of the diagonal elements. Now I min and I max should be the same as I1 and I2, as I said. And here I use the arctangent of the elements of first column and the second column, and I get the angle of them, theta 1 and theta 2, convert them to degrees. So if I run these lines, you'll see that one of them, theta 1, is the same as the theta p that we had, correct? And of course, we converted it to degrees, and that is the same angle, right? And the other one is 90 degrees behind that, and that is because these directions of these eigenvectors or the principal axes are always perpendicular to each other. So the direction of I1 and I2 are perpendicular to each other as they should be, and you see I can get the angle also through here. So the theta 1 is the same as what? Theta p, and theta 2 is theta p minus 90 degrees or plus 90 degrees. So you see I can solve the whole problem by simply using eigenvalues and eigenvectors of the inertia matrix, as opposed to what? As opposed to using all of those trigonometry formulas. Okay, so what's the good thing about this new one? The good thing is if you have a 3D, so your eye has all 9 components, then it's not so simple to use one simple angle. Because in 3D, you cannot rotate a frame with one single angle. In 2D, yes, you can rotate xy to get x prime, y prime by a single angle about z-axis. But in 3D, you have 3 angles that you can rotate, theta x, theta y, theta z, and then these moments, these 9 components of the moment will be functions of all those angles, and now finding the optimum set of all 3 angles to set the product to 0, all 3 products to 0, or maximize, minimize, and one of them will be the average of the 3, that is not as easy. So if you're dealing with 3D systems and your inertia matrix has 9 components as opposed to only 4, I do not recommend trying to formulate it like this with these trigonometry formulas. The best way to do it is just form the inertia matrix, which is 9 numbers, and then use the eigenvalues and the eigenvectors. And clearly, the eigenvalues are the numbers of the lambda matrix, because remember, your lambda matrix is going to be a diagonal, so it has 3 diagonals, and one of them is min, one of them is max, one of them is the kind of in between. And you have 3 vectors here, v1, v2, and v3, the columns of the v, and those show the direction of the 3 lines for these 3 major axes. Okay, so this is how you do it in 3D. Now, if I ask the final question, where would you use these principal moments? You find them, fine. Where would you use them in real life? Well, there are lots of places in real life that you can do. Use them in machineries like flywheels and turbines. One of the things that you want to do is to make sure that the moment of inertia is aligned with the principal axis. Otherwise, you are going to get imbalances and unnecessary oscillations, which will wear down the machinery. Okay? For instance, your flywheels are designed such that the principal moments of inertia matches the expected rotational axis to optimize the energy storage and reduces vibrations. In structures, similarly, when you design the beams in the bridges, you make sure that the moments of inertia align with the expected load directions. I mean, if you look at the beam, right? So if you look at this beam here, a simple cantilevered beam, so, and this is the load, some kind of load. You know that here, how should I put this beam under this load? Let's say this is H and this is W. How is it good to put it there? And let's say H is bigger than W. Is it good to put it like here, or is it good to rotate it like this, where H comes here and W goes there, and put it under the load like this one, rotate it 90 degrees? Or is it better to rotate it some other angle, 45 degrees or something, and put it under the load? Which one of them is better? And you'll find that in this case, this first one is the best one to do for the orientation of the beam. Because what matters in this beam is I about this axis, perpendicular to the load, and you want to maximize the I about this axis, which is the axis of bending. So you want to have the maximum. Now, in the case of a rectangle, that's so easy. The principal axes are already the ones that are passing through the axis of symmetry like this. And between these two, this one here is bigger one. If you watch my previous video, you see that, because for this one, H is going to be to the power 3. For the other one, W is going to be to the power 3. So this one is the biggest one. And so the stress in a beam is moment or force, let's say if it's a cantilever beam, times y, the height divided by I. So the bigger the I, the smaller the stress. So you want to maximize the I. And clearly in this case, none of these rotated versions are going to have as big I as this one does. Now this is for if it's simple, it has two axes of symmetry like that, and you know one of them is max, one of them is min. But if the cross section was different, so it was some arbitrary cross section like that, now how would you orient this beam? And it is under some load. Which orientation is good? This one, or some arbitrary rotation like that? How would you know which one is good? Here, you have to find the centroid. You have to go with the traditional x and y, find ixx, iyy, ixy. You can do it in CAD. And then plug it into the formula to find that the best direction in this case might be this one. This is the direction for it. This is basically about this axis. And if you look at this, this is your I max. And this is your I min. So it's better to put it something like this under the load, because about this axis you are going to have the maximum I. It gives you the best direction to put the beam under the load. Okay? Or whenever you want to, in robotics, you have some of the moments is equal to I times alpha. If this moment is limited and you want to have maximum I, you want to have maximum alpha, you want to have minimum I. So you need to find the direction that gives you the minimum moment so you can have maximum angular acceleration if this guy is fixed or constant. Okay, so knowing how to minimize or maximize I, in which orientation you should do it, that is going to help you in statics, dynamics, solid mechanics, and so many other places. And one other way that is these formulas and everything is analyzed is called the Moore's circle. And we are going to look at Moore's circle later when we talk about stress and strain transformations in plane. We're going to get formulas very similar to this for stress and strain transformations due to rotation of an angle theta. And then I will talk about the Moore circle, which is a pictorial way to show these but versus each other as opposed to versus angle theta. Okay, so one of your axes is going to be your normal axis, the other one is going to be your shear, and we'll talk about it later, not right now. But hopefully you learn how to calculate principal moments for a 2D case and what a 3D case in general. The best way to do it is using eigenvalues and eigenvectors. Thank you so much, and I'm going to see you in the next video.